Guys, let's get started. So I cannot use the mic. So can you hear me? It's okay. Okay. So the exam scores are out, right? So you can check your midterm exam score on the Blackboard. Then also you can check the median and then the average score on the Blackboard, right? Okay. And then so actually because the exam scores were out the previous night. So I did not check I did not analyze the exam scores. I will analyze the exam score later. Okay, so but for this course, so you can get a grade if you complete, if you take all exams, and then if you submit the all homework, then lab assignment, and you can get a grade. Okay. Okay. So please do your best until the end of the semester. Okay. Okay. Uh, so I recorded the previous class, and then I believe everyone watched the recorded video. And then so I posted the lab assignment. So in the lab assignment, you are requested to design data path element, right? So actually, for this data path element design, I already explained some how to design these hardware components during the class. But so actually, so in this time, so I will just explain why do we need we need to add the clock signal in the register file and data memory. Okay, so think about this. Think about this command, right? This instruction. So what's the operation of this instruction? So this instruction reads the operand data from register file and apply the addition for the x1 data, and then the sum of these two x1 data is updated to the destination register, also the x1. So actually this logic looks like this. So this is a register file, then this is the x1 and x1, right? And then we just perform add operation, and then this add operation is written back to the also x1, right? So think about this. If there is no clock signal, so so in the register file, the write process of of a register file is synchronized with the clock signal, right? But if this write process is not clocked by this clock signal, what will happen? So it becomes the 2x1, right? And then this updated value will be updated to the x1. So return back to the x1. And then in the hardware design and then in the RTL design, if the input signal values change, then this hardware, this component will work. So this register file will generate the 2x1 value, 2x1, then for this post, this output, and then so 2x1 plus 2x1, so it becomes the 4x1, right? Also, the value is updated, and then updated value is returned back to the x1 also, and then updated value is given. So this hardware will work. So it becomes the 4x1, 4x1, and then it will be repeated again and again. And then this is called a combinational loop. Okay, so this register file is the So if we do not use clock signal for the write process, so this register file is combinational logic, right? And then if the combinational loop is generated, then values are updated again, again, and again through this loop. And we need to avoid this case actually. So if the combinational loop is generated in the hardware design, then this hardware will work unstably. So we cannot guarantee the exact value, the exact output of this hardware. Okay. So in order to avoid this combinational loop, so we need to add the clock signal in the write processor. So we can that the write process is performed on the rising edge of a clock one. Okay. So by doing this, we can avoid combinational loop. So we can avoid this unstable case. Okay. So and then data memory is also the same. So for the data memory has the input and output port. So which means that the data will be read from the data memory, and then also we can write data to this data memory. And then so in the data memory, the write process is also synchronized with the clock signal in order to avoid this combinational loop. So during the class, so I did not explain about this clock signal in the register file. So I just explained this one. Okay. So and then also I believe you can do this lab assignment without some difficulty because I already explained. But so as you know, so in this lab assignment, you need to support the board instructions like this. So ALU is different. Okay. So ALU needs to support the board instructions, but I already provide this decoding rule. So because the ALU operation mode, okay, ALU operation mode by ALU OP, then OP code here. Okay. So actually, so this ALU is support the I-type instruction. So actually in the textbook and then during the class, so we have only one the I-type instruction like the load word, right? So and then load word is the load type instruction, right? So we can identify load instruction using this OP code field, and then if the OP code field is 000011 or 100011, so these are the load instructions and store instruction. Then we can just set ALU pin like this. Okay, and then for this case, then ALU control is this. But so in this lab, so this ALU needs to support the arithmetic and logic immediate time instruction, like the add I, exclusive or I, and I, this. Okay, so and then these instructions have different open code field like this. So you need to support so this ALU supports the four instructions like add I, exclusive I, and I. But actually, so for this design, you don't need to consider this case. So we can just consider this ALU control signal, right? And then based on the ALU control signal, then we can define the function of ALU, right? So actually, so in this lab, I kindly provide the skeleton code, right? Skeleton value code, and you can just complete inside of this Verilog module. Also, I provide the test bench file, right? So you can use the validator, and then you can compile your system Verilog module and the test bench file, and then you can generate the compiled binary file, right? And then if you execute these compiled binary files, then you can get waveform file. Then the output is the PCD file. And then also, actually, you test bench file is the C++ file, right? C++ code. And then which means that we can use any C++ function, right? Like the printf. So you can also observe the printf statement in the test bench file. Okay, so you don't need to design the test bench file. Okay, but you can just read how to design the validator test bench file. Okay, so actually, so this is the another. So if you took the digital logic design course, right? Then actually, in the previous semester, so we used the COSE value, and then actually the test bench is also is written in system value. But in this course, so we are using validator, and then actually the validator converts the system value module into the C module, C source file, right? So we can write the test bench using C++ code, okay? And then using this C++ test bench code, and then compile the converted the Verilog source files, and we can generate the binary file, and then we can just execute this binary file. The advantage of validator is that the simulation is very fast compared to the system Verilog simulation. So it is because, so the C is very fast. So C is much faster than any other programming languages, right? And then the validator just convert this system Verilog file into the C file, right? So it means, and then so if we generate the binary file from the C source files, then this binary file will much faster than the normal system Verilog simulation and some other code. Okay? This is the advantage of the validator. But the concept is a little bit different. It is because C code, the C programming language is not designed for audio design, right? So it means this C code cannot support some features of system Verilog. So this is the disadvantage. Okay, but if we can convert the system Verilog module to this C module using the validator, then we can perform the system Verilog simulation very quickly. Okay. So I briefly explain about the lab assignment. So and then in the previous class we complete the single cycle processor design. And then if you watch this video, then what is the disadvantage of this single cycle processor design? I mentioned performance issue. So right. So in order to understand the performance of the processor, so you need to understand the digital design concept. Now I already explained about the digital design concept and the conventions, right? So I logic determines the TC, clock frequency, clock period, right? Because the clock period needs to be greater than this delay of critical path. Okay, so in this design, so I already explained, but so in this design we can just calculate, we can just estimate the critical path of this design. The critical path is the load word. So it is because in order to execute this load word, the processor needs to access the instruction memory. So we need to add the delay of this instruction memory, and also we need to access the register file for read operands, okay, for reading operands. So we need to also add the delay for this register file, but this is for read of the register file. Also the box, so it just pass through this multiplexer. The multiplexer also needs to be, the delay of a multiplexer also needs to be included, but just ignore. Then the load word. When the load word is expected, the address needs to be calculated. So we use ALU for this address calculation. So the T ALU needs to be included, and then it access the data memory. So the T data memory, and then the result is written back to the register file. So this write delay for this register file needs to be included. So this is the critical path, the slowest delay of this single cycle processor design, and then TC. The clock period of this single cycle processor is to be greater than the sum of these delays, right? So if the TC is large, then performance will be degraded. So there is a performance issue in this single cycle processor design. Okay, so we need to improve the performance of the processor using pipelining. Okay, so actually this pipelining concept is not difficult, because we are already using this pipelining concept in our real world. Okay, so also in the real world, the performance is a very critical issue, right? Then actually, so we already applied, we already employing this pipeline concept at the real world. Okay, so let's think about this analogy, the pipelining analogy. So this analogy is very popular because I am using the textbook written by David Patterson, and then actually this textbook is very popular. Okay, so it means this analogy is also very popular. Okay, think about the laundry process setup. Okay, and then actually for this laundry process, actually let us assume that this laundry process is composed of 4 steps, right? So we need to use the washing machine, then dryer, then we need to fold the clothing, then we need to store the washed clothing, the clothing. Okay, so there are 4 steps, and then let us assume that for each step it takes 30 minutes. Okay, so just half hours. Okay, so and then these are tasks like the loading. Okay. So in order to perform this task A, then we need go through these 4 steps. Okay, and then each step will take 30 minutes. So in order to complete this task A, then it will take total 2 hours. Okay, and then after that we can start the next task. Okay, so this is the single cycle processor, right? So then it will take another 2 hours, then another 2 hours for the next task, then another 2 hours for the next task. So in order to complete these 4 tasks, the laundry will end at 2 a.m. So we want to avoid this case, this situation, right? So what's the problem? So we want to reduce this execution time of 4 tasks. Okay, so there are many tasks here, right? Then, so in order to execute these 4 tasks, then because so in order to complete the one task, single task, then it takes 2 hours. So in order to complete these 4 tasks, it will take 8 hours. But it takes so long. So we want to avoid this situation. And what's the problem? So how can we reduce? Okay. So if we just analyze how a single task is performed in this laundry process, then we can just observe that there is washing machine here, and the washing machine here, washing machine here, and washing machine here. So we can use washing machine, this washing machine, for 30 minutes out of 2 hours of this task completion time, right? The single task time. What's the problem? Washing machine is only utilized for this 30 minutes, but for this 1.5 hours, washing machine is idle. So we do not use washing machine. So this is the waste of resource. Okay, because washing machine is just used only 1/4 of the total execution time. Okay, so how can we avoid this situation? We can apply the pipeline. So pipelining idea is that so if task A complete using this washing machine, and then we can just move this task A to the next step. And then if the task A is moved to the next step, then this washing machine step is idle. So which means this washing machine can receive another task, like next task. And then if this task B complete using this washing machine, then washing machine can receive another task again. So actually the execution of this task can be overlapped. It is because we can just this task, a single task is composed of multiple steps, right? And then each steps are not overlap. Only the task execution time can be overlapped. 2 hours. But what is it different? Task B can be given to the washing machine after 30 minutes. So task B will start quickly, earlier. Okay? So it will take 2 hours. But because the task B starts earlier, the task B will be complete earlier. Right? So there are 4 tasks here. Then if we just apply a pipeline manner, then it will take only 2.5 hours, right? So we can reduce the total execution time using pipeline, right? So this is the pipeline concept. So the pipeline concept is that in order to execute the one task, so it will take a long time. But if we split this the task processing steps, then we can just split these steps into the pipelining steps, and then each step can receive another task if the current task is complete. Then the task can be given to the next step. So and then I mentioned that this pipelining is already employed in the real world, right? So think about the conveyor belt in a factory. Okay. So actually, for example, in the car manufacturing, so actually it will take very long time to complete the entire car assembly. But actually, you can observe the pipeline, and then there are many workers in the pipeline. Only this one worker only focused on only a certain job, only one job. And then if this job is complete, and then this job is given to the next person, next worker. And then actually the new job is given to this worker, and then this worker just does his own task. Okay, so this is the conveyor belt in the factory. Actually, so we use this conveyor belt system in order to improve the performance of a factory, right? The same to the processor design. So I mentioned that the single cycle processor, the problem is the performance issue. The performance is low. So it is because the single cycle processor, this is the clock period. Okay, so as I explained, enough to execute the load order instruction. Okay, so and then we need to add all combination of delays, right? And then the clock period is to be greater than the sum of these combination of delays. So in a single cycle processor design, then clock period is 1. But in the pipelining design, pipeline architecture, actually, if a single task complete its step, the first step, then this task can be given to the next step, right? And then this processor is synchronized with the clock signal, right? So this becomes the PC. Okay, so the delay of this single step, beside the clock period. you know, the in this example, the clock period is 30 minutes. Then for this design, the clock period is 2 hours. So think about the performance equation. The TXA, instruction count, CPI, and then TC. So we can reduce the TC part using pipelining design. Okay. And then also, by through this analogy, we can also understand. Oh, pipelining is better. It's a better design, right? We can reduce the total execution time. Okay. So actually, we can apply pipeline design if we can split a single task into the multiple steps. First, this is the first condition. So if we can divide a single task into the multiple steps, and there are many tasks, right? So as you can see, there are 4 tasks here. We can apply pipelining design. Right, if there is only a single task, we cannot apply the pipeline design, because if we just focus on the single task, for this single task, the execution time of a single task is the same. Okay, but if there are multiple tasks here and here, in this example, there are 4 tasks, then we can benefit from pipelining design, right? Can reduce the total execution time. Then, because we can reduce the TC also. So, the processor received the many instructions. Okay, so actually the program is compiled, and then so we already know that if the high-level language code is compiled, many instructions are generated, and then a processor execute these many instructions sequentially. Okay, there are many tasks, and then in the single cycle process design, we know that in order to execute a single instruction, and then there are multiple steps, the 5 steps, right? So instruction fetch, instruction decoding, execution, memory, and write back. So we can apply pipelines to this processor design. For what? Not improve the performance, right? Because we can reduce the TC. Okay, so risk 5. So as I mentioned, there are 5 steps, 5 stages. So we can apply the pipeline stages of this single step or a single step. So which means, so like this analogy. So in this analogy, the single task composed of 4 steps, but in a risk 5 processor design, there are 5 steps. Okay, and then we can apply a single pipeline stage to this a single step. Okay, so like the instruction fetch, instruction decoding, execution, memory, and write back. Okay, so then let's think about the pipeline performance. Okay, so actually, in order to design a pipeline processor, we need to balance. We need to balance the delay of each stage, so each step. So it is because the critical delay lies the clock period. And then, so why clock period is critical? Why is it important? So it's because of this equation, right? So I I wrote this equation many times. Right? Why clock period is important? It is because of this equation. So in order to increase the performance, we need to reduce the clock period. It means we need to increase the clock frequency, right? So as I mentioned, we can simply compare the performance of the processor using clock frequency, right? So each stage, the delay of each stage needs to be balanced. If not, the longest delay will size the clock period. So for example, so let us suppose there are 5 stages here, and then delay of execution is 500 picosecond. This is 100, this is 100, this is 100, this is 100. The problem is that the total execution time in a single cycle processor is the 900 picosecond in this case, but if we just apply the 5-stage pipelining into this processor design, the longest stage, the stage that exhibit the longest delay besides the clock period. So in this case, this is 500 picosecond. Okay. The problem is, so in this analogy, if there are many tasks, then we can increase the performance by 4 times, right? So speed up is nearly 4 compared to the single cycle design. It is because in order to receive one task, and then it will take 30 minutes. But for the single cycle design, so it will take 2 hours. So actually, this processor, this design can receive every task for every 30 minutes. But this design is to receive a single task every 2 hours. So speed up is 4. But in reality, the longest delay of the pipeline stage besides the clock period. So it means the delay of each stage is to be balanced. Okay, so in this example, this is the 500 picosecond. So actually, the speed up is 9 divided by 5. Okay, 1.8. So, but if we just apply a 5 stage, then the expected maximum speed up is 5. Okay, so compared to this ideal, the expected speed up 1.8 is very low. Okay, so it is a bit, so the delay of each stage is to be balanced. Okay, so this is the example. So actually, this is the extreme case. So extreme example. Okay. So in this example, this is it's a stage of the pipeline architecture, and then so you can find the delay of each stage. Then what is then this is the total execution time if we use the single cycle processor. So in this example, so this example also shows that the load one is the critical path. Then what is the clock period of this load one? This single cycle processor? Clock period needs to be greater than 800 picosecond. So we can just assume that the clock period is around the 800 picosecond. This is for the single cycle processor. And then we just split this single cycle processor into the 5 stages. Then we can apply the pipeline design to the single cycle processor. And then each column represents the delay of each stage, right? Then what's the longest delay? The longest delay is the 200 picosecond here. Okay? So then I mentioned that the longest delay of a stage besides the clock period, right? So in this case, what's the longest delay? 200 picosecond. So we can assume that the clock period of pipeline processor is 200 picosecond, right? So what's the speed up? Based on this equation, if the instruction count is the same, because this is the software part, and then CPI, so we don't know the CPI, but for the ideal case, the CPI is 1, right? Because, so like this case, the processor can receive one instruction every cycle. So this is the ideal case. So let us suppose the CPI is 1. Okay? And then also for the single cycle processor, CPI is 1, right? Is it different? So what is the speed up? Speed up is 4. Right. So for the single cycle processor, TC is 800 picosecond. Then the pipeline processor, TC is 200 picosecond. So only this part is different. But why? So we just apply 5 stages, right? And then, so in this analogy, so we apply 4 stages. So expected speed up is 4. But in this example, we applied 5-stage pipeline architecture. So it means based on this analogy, the expected speed up is 5. But why 4? It is because the delay of these pipelining stages are not balanced. Okay? So you can find the 100 picosecond and 100 picosecond here. The delay is different. Okay? So also, if we just check the execution time of one instruction, the execution time is actually, it becomes the 1000 picosecond. So this is because we need to use the same clock signal for each stage. So the clock period is 200 picosecond. So it means that for each stage, it will take 200 picosecond, the pipeline design. So the execution time becomes the 1000 picosecond. But as you can see, the speed up is 4. So this slide shows how the instructions are executed in the single cycle processor and then pipeline processor. Then so as I mentioned, there are many instructions, which means there are many tasks. In a single cycle processor design, in order to execute the one instruction, so we did take 800 picosecond, which means that we need to wait for 800 picosecond if the instruction is given to a single cycle processor. But if we just apply the pipelining design, you can find that each instruction can be given to the processor every 200 picosecond, like this. Okay, so we can increase the performance. Okay, so the speed up, if all stages are balanced, so which means that if we can make the delay of each stage, delay of stages equal, okay, it means the balanced, the all take the same time, all stages take the same time, then the speed up is same to the number of pipelining stages, right? Okay, so like the laundry process analogy, so if we just apply n stage pipeline and then the delay of all stages are the same, then we can just divide the clock period to the 1 over n time, right? So it means the expected speed up. The expected speed up is same to the number of pipelining stages, right? So n. But the condition is all stages take the same time. Okay? So it means the delay of all stages are the same. But if they're not balanced, the speed up is less. So as I explained, okay? Because the longest delay, the stage that exhibit the longest delay will decide the clock period. Okay? Then speed up is due to increase the throughput and latency. Because if we just check the latency, so what is the latency? The time gap between the start of a task and then the end of a task, right? So if we just check the execution time of a single instruction, then the latency can be, in the best case, the latency is the same, or the latency can be increased, right? So like this example. So if we just check the single instruction, the latency becomes the 1000 picosecond. Then for the single cycle processor, it's 100 picosecond. But if we just check the throughput is improved, which means within the same time, more instructions can be executed. So throughput is improved. Okay, this is the pipeline design. Okay, so then this slide explains that the RISC-V ISA is designed for pipeline. So which means, the instruction set is simple. Okay? So it's a RISC type. So it is because the x86, so x86 is the complex, so it's a complex instruction set. Then the instruction format is very complex. Okay? So which means in order to decode an instruction, then we need to use the very complex hardware. And then if we use the complex hardware, the delay of this complex hardware will be high, it's large. Okay, so which means the clock period can be increased. Okay, so but if we just use a simple encoding rule, the instruction design, if we learn about the instruction design, right? So encoding rule from the assembly instruction to the machine instruction, right? And then actually this encoding rule is regular and simple, right? So this is because the reason is that if we just apply the regular encoding rule, then we can implement simpler hardware, and then simpler hardware delays low. So which means we can increase the clock period. So this slide just explain this. But as I mentioned, even though the x86 machines, x86 machines also employ RISC-like architecture. Okay, so that's why the Intel CPU, the clock frequency is very high, right? Even though the instruction set is very complex, but clock frequency is high. So there are many factors like the architecture design, the hardware design, and then also the semiconductor technology. There are many factors that can determine the clock frequency. But the main reason is that even though the Intel uses the complex instruction set such as x86, but the architecture is similar to the RISC type architecture. Okay? So we can decode the part, even though the pipeline stages, there are many pipeline stages, but the clock period is low. Okay, oh, it's very good. It's very good news. With the pipelining, we can increase. We can just increase the performance of processor. Okay, but pipelining also has the disadvantage. It means that when I explain about this execution time equation, I see CPI, then TC, and then with the pipelining, then I explain that we can reduce TC, so we can increase the performance, and then we assume that instruction count is the same because the software is the same. Then CPI is 1. Okay. Because the single cycle process design, CPI is always 1, right? For what we can, single cycle processor can execute 1 instruction per cycle. But the pipeline, the architecture, CPI is not 1. So this is the disadvantage of pipeline architecture. So usually because the TC is improved, the TC is reduced, we can improve the performance. But this part can be larger than the 1. Okay? Larger than the 1. Okay? The pipeline architecture. So we learn why. Okay? So this is the very important part. So I will explain about the Azure. Okay. So Azure. So actually, the actual meaning of Azure, the real world is like this. So very plain surface. So then there can be a crack here in the ground. So if we just encounter this crack, then let us assume we are running, but if we just encounter this crack, then we need to reduce our speed, right? Because we need to handle this situation, right? Actually, the meaning of Azure means this crack, okay? This crack in the ground, in the real world. But in a CPU, CPU, the processor design, the hazard is the as the different meaning. Okay? So what is the hazard? Hazard is the event that waste clock cycles. What does that mean? So, in this, in the process of design, we until now we assume that a processor can receive instructions every cycle, or an instruction per cycle, right? So which means that the processor does not stop. Plus, a processor actually regularly receives instructions per clock. Okay, this is our assumption, but actually, because of some reasons, a processor cannot receive an instruction per cycle. Okay, so which means clock cycles can be wasted because the processor cannot receive an instruction, right? So in this case, in this clock period, the clock cycles are wasted. This is the hazard. So you can just understand that hazard is the something event that wastes clock cycles in a processor. Okay. So there are three types of hazard, like structure hazard, and data hazard, and control hazard. Okay. So also this is very important. So you need to understand the reasons of hazard. So it is because if we can understand why clock cycles are wasted, then we can create an idea that can avoid these hazards, right? So that's why it is important to understand the reason of hazard, right? So there are three types of hazard: the structure, data, and control. So actually, this word represents the reasons of hazard. Okay, the structure hazard is that. So it is this hazard is caused by some structure issue, like the hardware resource issues. Data hazard. So this data hazard is caused by data, like the data dependency. Okay. The control hazard is caused by control instructions. What are control instructions? Branches and jump instructions, right? Okay, let's learn about the three different types of hazard. Structure hazard are caused by conflict of use of a resource. What does it mean? So this is the hardware, hardware component, okay? And then a certain task try to use this hardware. Okay? It take time, delta t. So during this delta t time, this hardware resource is occupied by this task only, right? So during this delta t time, this hardware cannot be used by other tasks, right? world, okay, hardware resources is limited. We have limited hardware resources, and then if a certain hardware resources occupied, then other tasks cannot use this hardware. Right? We cannot copy this hardware, right? So this is the structure hazard. So it means there are multiple tasks here, multiple tasks are here, and then multiple tasks are trying to use the same hardware resource, and then but because this hardware resource is already occupied by this task or certain task, then this task cannot use this hardware resource. So in this case, this task is to wait. The wait means that clock cycles are wasted. So this is the structure hazard. Okay, so which means multiple tasks is to use the same hardware resources, but the hardware resources already occupied. So the next task cannot utilize this hardware. So actually, in the pipeline architecture, you cannot observe a structure hazard. But in a real processor design, we can observe many structure hazards actually. But in a single 5-stage pipeline design, the structure cannot observe structure hazards because the structure hazards are already reserved. So actually, in a single cycle processor design, we split the instruction memory and data memory, right? All instruction, in order to fetch instruction, then we need to access the instruction memory. So which means that all instructions is to access the instruction memory, right? So like memory. And if an instruction is load word or store word, so it's a load or store instructions, these instructions need to access the data memory. Okay, so we in a single cycle processor design, we separate the instruction memory and data memory. But if we just use the unified memory, like one memory, right? Then all instruction is to access this memory. So memory resource is occupied. And then if this instruction is load word or store word, then you need to this instruction is to access the memory, but this memory is already occupied. So in this case, if the instruction is load word or store word, this instruction needs to wait for one cycle. So wait for one cycle, it means clock cycle is wasted. Okay. So in order to avoid this situation, that's why we split the memory into the instruction memory and then data memory. So even though this instruction memory is occupied, load word or store word can access the data memory. So I already explained that instructions are also stored in the memory space, the same memory space. Okay? But so it can be you may not understand the situation, but actually, so this is the cache, that real memory. So we will learn about the cache later. So just understand that in the processor, the instruction memory and data memory is separated, not to avoid the structure hazard. Okay. So then in this simple pipeline architecture, so we do not observe the structure hazard because structure hazards are already reserved. But in real hardware design, we can observe any structure hazard. Okay? And data hazard. So this is important actually because the structure hazard are already reserved, but data hazard, the data hazard is very important in the process of design because the main source of performance degradation because of hazard is caused by data hazard. Okay? Then what are data hazards? Data hazards are caused by, as I mentioned, data dependencies. Then what is a data dependency? So like this. So you can find the add instruction here and solve instruction here. And then X19, so this is the destination register of add instruction. And then the following solve instruction is to use the result from add instruction. I mentioned that this situation is very frequent. So because we write the code like this, right? So A equals B plus C, and then T equals A plus 1 like this. Okay? And then data dependency. This is a very frequent. Okay. So what's the problem? Actually, in the single cycle processor design, we don't need to consider the data dependencies or data hazard. So it is because if this add instruction is executed in a single cycle processor, then all steps are complete within one clock. So X19 is stored in the register file, and then after that, solve instruction will be received. So solve instruction is given to a single cycle processor, then it will be executed. So we don't need to consider the data hazard in a single cycle processor, but the pipeline architecture, we need to consider the data hazard. Why? It is because X19 will be returned back to the register file, the write back stage. And then actually write back stage is the last stage of the 5-stage pipeline architecture, the last stage. But the solve instruction needs to read X19 data when ID. So actually, if this is the solve instruction, then instruction fetch, ID, and then execution, memory, and write back. Okay, then what's the problem? Oh, the add instruction will write the data, the write back stage. So this is a time, right? But solve instruction needs to read data at this time. So this is the future, this is the past. This is not possible in the real world, right? So this is the future event, this is the past event. So actually the solve instruction cannot start at this point, right? Because of this issue. So because of data dependency. So in order to generate the correct result, server instruction is to wait 2 cycles, then server instruction can start at this point. So 2 cycles are wasted. So this is the data hazard. So data hazard, the clock cycles are wasted by data dependencies. Okay. Then in the pipeline architecture, this event can happen actually very frequently. Okay, so you need to understand this. Then so actually I will explain about the other hazard the next class. Okay, then I'll start here in the next class.